All right, so let's work this problem. We want to find the slope and displacement at B. And you can see EI is a constant, so that's one less thing you have to deal with. You don't have to actually do the calculation. There's not a numerical value for those. It doesn't say which method. Now, we're talking about virtual work, so it's probably going to be the preferred one. But let's just examine it quickly and see if other techniques would work. Let's start from the beginning. What about direct integration? Can we do direct integration on this problem?
Oh, yeah.
I think the answer is yes, because you can write a single continuous moment equation for this problem. Another interesting thing is since the fixed connection is over here on the left side, that's usually where x is 0, so your two integration constants would be easy to determine. So this would be a very doable problem with direct integration. And then all you have to do is evaluate your two functions you found at 3 meters, one for displacement and then one for slope. Okay, so that's a go. What about conjugate beam? Well, what kind of moment diagram will this produce? Something nice and simple and regular?
Yeah.
No. It will be a very odd-looking parabola. And you probably don't want to deal with that. So it's doable, but really probably not in the scope of an exam. So then the other solution process that would be probably reasonable would be virtual work. So what do we need for virtual work? Let's do that one first. So I am going to need a moment expression for the problem. Can I write one for the whole structure?
Yeah.
Well, sure. We just talked about it. So that stage would be identical. You have to write a moment equation to get started for virtual work here, and you would also need it for direct integration. So right now it's a tie between those two. The other thing I'm going to do is, to save some time, since it's a cantilever, that's convenient in that if I cut the structure somewhere and decide whether I want the left side or the right side, the left side would be easy in terms of finding x and all that, but I would have to find reactions. So I'm going to choose the right side, because I don't have to find the reactions. So let me quickly redraw this free body diagram of a section to the right. So I would have my 400 Newton force, and then I would have this distributed component, which has the intensity of 300 newtons per meter, and then I'm making this cut at some distance from the left, x, so the segment to the right would have a distance of the total 3 minus x. And then at the cut, what am I looking for? My internal moment. So I'm going to resolve my distributed force into, I didn't give myself a lot of room here, I'm sorry about that, into a concentrated equivalent. I'll just call it F. And I'll come over here and compute F. What is F? Well, it should just be the area under this part of the curve. It's a rectangle, base times height. So that will be 300 times 3 minus x. And then the distance from the cut to the centroid, D, will be half the total, or 3 minus x over 2. So far, so good?
Yes.
All right, so let's sum moments and find what that is. So I'll sum moments at the cut, make sure I'm in equilibrium. So I'm using right-hand rule for my sign convention. What kind of moment is this, positive or negative? It is negative. And the force F about the cut surface, positive or negative moment?
Negative.
Negative. So that would be a force of 300 times 3 minus x times a distance of 3 minus x over 2. What else do I have? I've got this 400 Newton force, which is the distance also 3 minus x away, and it creates what kind of moment? So that will be 400 times 3 minus x. So it looks like the moment as a function of x is going to be what? I think I'm just going to collect some stuff. So this half takes away that, right? So that'll be 150 times 3 minus x squared. And then that, I guess you could run that out if you wanted to, or you could just leave it. So there's my real moment. Is there any place I can check that to see if it works in this structure? What's the moment out here on free end? And that would be at x equal 3. If you put an x equal 3 here, you get 0. Now, if I had found my reactions and I knew my bending moment at A, I could plug in x equals 0 here, and I could probably get that value. But I don't have that information. But I will write here that at x equal 3, it should be 0, and that is confirmed. So I've got my real moment. Now what do I need to get? My virtual moments. We'll do displacement first. So I want the displacement at B, that's the free end. So let's quickly draw the virtual beam. So there's the beam. Where should I put my virtual force? Yeah, at the point you want, which is B, and you think it's going to go up or down?
Down.
Why not? So there's my virtual force at the point I want B, assuming the direction I want is down. I'm going to follow the same strategy I applied above, in that if I make a cut, I want to work the left side or the right side. Not that the left side would be challenging, wouldn't, but the left side would be a little more convenient. So I've got that. So I'm going to draw another free body of that here with my virtual load of 1. So I'm going to approach the cut from the left side at some distance x, and that will relieve. It will leave this segment x minus 3. And then what's the moment? Well, I'll assume positive bending moment. This is virtual moment, so I'll use the lowercase value. Well, that's not too bad. In fact, if I some moments about the cut in my virtual beam, what do I get? Well, the moment is, with this sign convention, positive or negative?
Negative.
Negative. The moment of the virtual force about the cut?
Negative.
Negative. So it has a value of 1 and a distance of 3 minus x. So it looks like the virtual moment is just going to be negative 3 minus x. Or x plus 3. I'm going to leave it like that because it kind of matches this other one up here. So let's do this. Can I check that? What should be the virtual moment at, say, x equal 3? The free end should be 0. And it looks like our equation gives us that. So again, that's confirmed. So what do I have to do now? I just have to multiply the real moment times the virtual moment and integrate it. So the displacement at B is the integral from 0 to 3 of the real moment, which is all that nonsense. Oh, I'm going to just stick the EI over here. That way I don't have to carry it around. So the real moment is minus 150, 3 minus x squared, minus 400, 3 minus x, times the virtual moment. I'm going to take that negative sign and run it through, and all these will become positive. And this will just be 3 minus x. Now, if we're working this problem on the exam, I could say, oh, that's good enough. That is the virtual work expression. Now you can see this is just wouldn't be hard, but it would be a bit tedious. If you expand this, you're going to get a quadratic, and then times that, you're going to get a cubic. I know you can integrate cubic functions, but probably along the way you're going to make a mistake. So it's just really not worth it. That would be good enough for me. Is that good enough for you?
Yeah, it is.
I like that.
Yeah.
I like it. You agree with me?
So, are E and I ever not going to be constant?
They can be. Since you brought that up, there was another problem I was going to work today that I decided not to do. It looks like this.
I like it.
As you notice, I is not constant. So you would have to write an expression from 0 to 6 where you have one moment, and then from 6 to 20 where you have a second moment. But when you integrate it, right, you would only be able to integrate from 0 to 12 divided by 2i, and then from 12 to 20 divided by just I. So you have to keep track of that. So you would end up with 3 integrals.
So that's similar to how when you have a different virtual load case than your actual load case? Because you have to have...
Well, that will probably always be true. What you just said.
Most of the time.
Yeah, most of the time.
But you have to do multiple integrals because of the different...
Well, this one you have to
where
do
the loads
multiple
are placed.
integrals because first you're going to get a moment that's different here, and then because of the point load, you'll get a different moment equation for the rest of the beat. So if this were a constant I, you would have 2 integrals. One from 0 to 6, and then from 6 to 20. But see what happens here about 12? It changes. So although the integrands for these 2 integrals would be the same, what would happen is the I would change on the second part. So these would look the same, except this one would be divided by 2i from 6 to 12, and then from 12 to 20 just divided by I. So you'd have to stop. Keep track of it that way. So it's unlikely, well, it's unlikely is not the right word. It's unusual that you would change material, like E would change. But it is common to change the cross-section I. Since you brought it up, I'll look through my bag of tricks and see. I think I've worked this problem in the past. I'll just go ahead and put it on the website as a problem that you can look at. It's going to be called 8b or 8b-2 if you want to look at that. All right, so we're not done, unfortunately. I need the slope too. So what do I have to do is I have to draw another virtual work set. So again, the geometry of my problem is the same. I have this cantilever beam. But what am I going to apply now? Yeah, I want the slope at B. That's out here at the free end. Positive slope would be created by a couple that look like that. Remember, we're assuming the force is dimensionless, but in this case it's force times distance. So this is going to have a weird unit of feet. 1 foot? Huh? Maybe it's virtual.
Do you mean meters?
Say again?
Do you mean meter and not foot?
No, I'm going to switch to units now.
Okay.
No. I'm going French. We're going meters. So we can apply the same strategies we did before. I can cut this structure anywhere I like. Look at the left, look at the right. I think the left will be easier. So when I draw my free body diagram of that, there's the right portion with my applied 1 meter couple at some distance x from the left. I have a remaining segment of my structure, which would be the length 3 minus x, and then internally I've got the moment. Now for slope we use this symbol lowercase m theta indicating that it's from a rotation. And now if I sum my moments about the cut, this won't take very long. The internal moment is, with this sign convention, negative m theta. And the applied force is positive of 1. So it looks like m theta is 1. So to write the expression for the slope at B, I'm now going to integrate along the length 0 to 3 the real moment times the virtual moment. And that just ends up being negative 150, 3 minus x squared, minus 400, 3 minus x, and integrate that. Now we can do a few things, kind of qualitative things. If you look at this integrand, you can see all the terms are positive. So this value for the displacement will come out positive, which means we assumed it went down, so that's the correct choice. The end of the beam is going down, and that makes sense. On the virtual slope, we assumed that a moment would create what kind of slope in the real beam? Positive. And look at our values. They're going to be negative. So we're going to get negative slope. Does it make sense at the end of this beam that it would be negative slope? I think so, because you're probably going to get a deflected curve that looks something like that. And you can clearly see here at the end that that's a negative slope. So that seems to be reasonable. Any more questions about this one? This was a little more doable in terms of actually running it out and coming with an answer. All right.